All right, we're back in action, part 3. Third part of this. And again, this is a problem. We're not using that new formula. We're using that old formula. First thing we want to do is define hypotheses and run the test on here. So think back to H naught and the alternative hypothesis, something we've been doing all year now. Great cartoon, by the way. It says here, we're testing whether the preferences are equal. Well, because there's two groups, if they're equal, that means they're going to be 50% for the entire population. And then if we're just checking if they're equal, there's nothing in here that suggests Coke or Pepsi is a higher percentage. We could look at the numbers up here. If I can get my little finger pointer on here, I guess I can't. I'll use the old school way. If we lose these, we could say, well, hey, Coke had a higher preference. There's nothing in the wording that suggests that, so we're just going to say they're not equal to 50%. They're not equally liked. If there was Coke, Pepsi, and, I don't know, Gatorade, this would be 33%, and this would be 33%. So just 1/2 for both of those. So in terms of outcomes of the test, then we go through the test and run through this in part C and check to see how this works out. So you find your standard error, which is basically half of that formula that we were just looking at a minute ago. You just need one set. And this is where we use the null to define those. We don't use these numbers up here. We're using the null hypotheses. So you multiply those out. Hopefully I do this correctly. And it doesn't matter. This is a question for later on. Don't worry about this yet. I believe this ends up being 2.2% standard error. Just using that single proportion formula for standard error. The thing you might be tempted to do is use your sample proportion. This is the percentage for Coke. And I also have the little subscript here for C on here. This could be Coke or Pepsi, either one, doesn't matter which one we choose on that. And the same thing, I put a C there. This is my percentage for Coke. I could put subscript there if I want for P hat. So 53% were Coke. So, running the actual test, it doesn't matter whether we use Coke or Pepsi. It would just change the number slightly in here. It would just switch the signs around in terms of which one's higher or lower. Not a big deal in terms of actually running the test. So hopefully you ran the test. If you didn't, again, I'd suggest you pause this. A little practice for running a hypothesis test. We want to see how far this away is from the null relative to the spread, the standard error, that distribution. So this is only 3% away, or 0.03 away. That's not that far. And we want that 0.03 relative to how spread out the data would be to get me a z value, a z statistic. I think if I do my calculations correct on here, it's between 1 and 2 standard deviations or z statistics away. I think it's 1.36. And if you remember from the last section, this is where we look this up in the table to find a p-value. Hopefully I did this right. If you didn't do that yet, take a pause. Look up your p-value table. I think it ends up being 0.836, maybe 839. Either way, the let's see, 10th, 100,000, the 10,000th place doesn't make a big deal difference on here. You'll notice I have a little 2 in parentheses. I'm supposed to double that because it was I didn't assume that Coke was higher. I assumed there was no difference on there. So maybe on a 10% significance level, that would be significant if it was a one-tail test. But if I double that, I'm going to be over 10%, which means it's not that significant. Coke is better, according to these 500 people, in terms of taste. But it's not significantly better. It didn't beat Pepsi by enough to really convince me on a 5% level or even a 10% level. If I change this hypothesis and I made it a one-tail test, it's significant on a 10% level. It's less than 10%. So this, according to the data, there's not a significant difference. Now, if I was Coke and I was running this, I'd run on a 10% level and say, hey, Coke's definitely better. Definitely proven to be a better taste. This was the old commercial in the 90s, back when I was a young Hess. All right, last one here. Give this one a try. Pause the video. See if you can analyze this carefully. Write a confidence interval. This is sort of the next section, getting you ready for that. If you don't remember confidence intervals, you're looking at a sample statistic plus or minus your margin of error. This, of course, is your margin of error based on how precise you want to be, a z value based on how precise you want to be. And And it says here we want to be 90% confident. So you got to read through this a couple times. And you got to pinpoint what you're trying to be confident about. It's the difference in proportion of women who get pregnant based on whether they smoke or not. So there's your two categories. Smokers and non-smokers, that's one category, and whether they got pregnant or not. So I've got to find a p-hat, or a sample statistic in this case, to analyze and a difference in those two. What percentage of people got pregnant? Well, 244 out of 678. I don't care about those. I want to look at the two different groups. 38 of 135 smokers got pregnant versus 206 out of 543. Now I'm looking at this. This is a small number relative to that. This is a little bit bigger. This is closer to 50%. I want to compare those two percentages. I believe I divided this correctly. 28% of the smokers got pregnant. And 38%, roughly, of the non-smokers got pregnant. The sample data is suggesting that there's 10% more likely, to get pregnant, or 10% less likely, if you think of it that way, if you're a smoker. So there's sort of a start to this one. I'm going to come back in the last part 4 of this video in a minute, just so these things don't get too big to download.